So, thank you for sharing past this year. Today we have Liam to be talking about applications of filtered THH.
Okay, nice. I think for everybody here who saw the website, the Young-HOM website, and thought I was going to talk about chromatic homotopy theory and topological restriction homology, I'm sorry to disappoint. I will not be talking about those things, but if that's what you came here for and you really don't care about what I'm about to tell you, I can probably say something about that at some point. Um, yeah, I guess today I wanted to talk about, I wanted to start by, telling you something about like what filtered and graded THH, or more generally Hochschild homology is. And then I want to tell you like why this might be sort of an interesting gadget that is perhaps even useful, that could like tell us some stuff about, examples of things, or it can help us prove theorems. Uh, and yeah, so that's, I think, the plan for the day. And if you like, please feel free to just interrupt me and ask questions. I will try to look at the chat as usual, but as I'm sure, as it's okay, Torgir, don't worry. It's no problem. I'll try to look at the chat, but maybe the organizers could help me if I'm not paying close attention and let me know.
Can do that, of course.
Okay, thank you. Yeah, so I should probably start saying some stuff now about math. Okay, so maybe I just want to start off like I don't know how comfortable everybody is with sort of the filtered perspective on things. It's definitely becoming like more of a kind of ubiquitous setup and technology these days, especially with the introduction of things like, I don't know, synthetic spectra or the even filtration or some of these new fancy gadgets that we have for doing homotopy theory. So maybe I just want to start with like one or two words about like sort of what's going on with filtrations and gratings, or what's the perspective that I want to take on these things for the purposes of what I'm going to tell you later. So, what are filtrations and gratings? In stable homotopy theory, these are things that we run into all the time, and there's a ton of examples that you can write down. So, maybe like the most canonical examples of like filtrations and or filtrations, at least, that you sort of run into in homotopy theory is probably taking the Postnikov or Whitehead tower um, of spectra. So, of course, this is a minor, okay, I shouldn't like grandstand and complain too much, but like people don't sometimes they do a really poor job of distinguishing between these two objects. They are legitimately different. Sometimes people call the Whitehead filtration the Postnikov filtration, and that bothers me a lot. Though I guess if you work cohomologically or you're an algebraic geometer, then maybe there's some reason to conflate those two names, but whatever. So, okay, what's the Postnikov filtration and what's the Whitehead tower? Um, it's the thing we get by sort of either successively killing homotopy groups in a spectrum or a space below or above a particular range. And we have a canonical functorial way to do this. We have these functors, these truncation and co-truncation functors, and these filtrations of a spectrum are obtained by sort of stitching all of this together. We get something for some spectrum X, we get some filtered spectrum, which looks like, I won't write everything out too carefully, but some kind of tower, which looks like this, and it's built by killing stuff below a certain range, and all of these things like include into each other. And there's a similar setup for this. Oops, I drew that the same way, and I just complained about conflating these things. So this is obtained similarly by kind of like, killing all the stuff above a certain range, and then, kind of keep going down and if you want, you can think about this first one as sort of an increasing filtration going from left to right. And if you can think about the other one as sort of a tower going from right to left, where you're sort of iteratively building things up versus kind of like killing stuff and including it inside. And we love these things. These give rise to a bunch of useful tools. For example, you can use these things to construct a THH reciproc spectral sequence. And maybe just as a very brief example, like if depending on what your spectrum looks like, you're going to get really different outputs when you consider the Whitehead tower of different kinds of spectra. So for instance, like if X is something like let's just say HFP, or more generally some Eilenberg-MacLane thing, then the Whitehead tower is going to look pretty boring. It's basically going to look like HFP sitting in degree 0, and then it's going to be the same thing in degree -1 and -2 and so on. And then it's going to be 0 going up this way. So it's sort of constant on 0 and all the negative integers. And then if it's something like KU, for instance, or non-connective K theory, then it's going to look a little bit more interesting, and you're going to end up with something that looks like a copy of connective KU in degree 0, and then some like even shifts of that successively up, where certain maps are equivalences because KU is even, and so when you take like an odd connective cover, you're not actually killing any like odd homotopy group. So these are going to look pretty different. Another example that stable homotopy theorists will know and love is, maybe I'll just say Adams-Novikov. So there are a few different ways to construct this kind of thing these days. Sort of the classical sort of way is to take some nice homology theory that you're interested, which is like maybe a commutative ring spectrum, and you form its Kobar construction, which looks like this. It's a big cosimplicial object, and it goes like this forever. And well, what you could do is you could sort of take the totalization of this thing, and that turns out, because by the Dold-Kahn correspondence, you can always write a cosimplicial spectrum as some sort of tower of spectra. This will basically give you something that looks like the I-adic filtration associated to a ring and an ideal. Where here, what we have to suitably interpret things. So here we're going to have a map from S to E, and then we're going to call I the fiber of this map. So this is a fiber sequence. And then the associated filtration you get is going to look like S in degree 0. It's going to look like a copy of I. It's going to look like 2 copies of I, and you're going to go up forever and ever. These days you can kind of do Adams-Novikov in a quicker way, where you do something like you take this gadget, and then you do something like the limit over the connective cover of this Kobar construction, or I guess 2 star, and maybe I'll say mu to be concrete. And this is kind of another way that you could produce this, and it has good properties, and it's like related to the even filtration. And I think this construction originally appeared in work of Pachkoria and Pistrogowski, if I remember correctly, but I'm not sure. Okay, so and then maybe just like maybe like a little tantalizingly, I'll sort of mention some of the there's this whole new game of like even filtrations, which I want to say nothing about today, and motivic filtrations on things like TC, TC minus, TP, etc. And there's a bunch of people whose names I should say, like Botmore Schulze, von Rexit Wilson, Liu Wang, etc. Okay, so all of these. So what is the point? What is the reason that we think about these kinds of filtrations? The reason we think about these things is that if we just think, for instance, about the Whitehead tower, this is basically some kind of way to try to interpolate going from purely algebraic information and algebraic structure to something about spectra. In this Whitehead tower, the associated graded is going to be a generalized Eilenberg-MacLane spectrum. If you take the successive cofibers of all the maps in the Whitehead tower, those are going to be like shifts of Eilenberg-MacLane spectra. And when you take the sum over all those things, that's going to be generalized. And working over those kinds of objects in stable homotopy theory tends to be much simpler. And so sort of the goal, or maybe the point of thinking about these filtrations is that these help to interpolate between, maybe I'll just say, things we kind of understand, which maybe you should think about as like the associated graded, and then things we'd like to understand, which maybe you would think about as sort of like the co-limit over this filtration or something like that. So it's the underlying object. And okay, so I should tell you sort of formally what all of this looks like with actual math, because I've just kind of written down a bunch of examples. But like from the perspective that we've just taken, like in all of these examples, what are filtrations? So filtrations they're pretty much nothing but functors which go from the category Z-op into spectra. And now here I'm giving the integers the poset category structure, and then I'm taking the opposite category. And so, for instance, the Whitehead tower is a great example of such a gadget. And what do I mean by a graded object? So gradings these are going to be functors from Z, but now with a different category structure. I'm going to throw away, I'm not going to work with the poset structure. I'm just going to think about it as a discrete category. So it's just object, all the vertices, and then just the identity self maps. And then I'm going to think about something like this. And the categories of these things we're going to denote by fil, sp, and ger-sp. And I should just mention that this graded spectra category is really the same as a product over the integers of spectra. So it's just literally like one spectrum for each integer, which makes perfect sense if you think about gradings. Okay, and these categories have really, really, really good properties. I'm going to say a bunch of words here, but essentially the point is that in these cases, the integers are symmetric monoidal categories just given by addition. And the symmetric monoid, and so formally this allows you to produce symmetric monoidal structures on the categories of filtered and graded spectra. So I'll just say filtered and graded spectra are, stable, presentable, symmetric monoidal categories. And this is great because this is a place in which we can do homotopy theory. We sort of know how to do all kinds of manipulations here. This is really nice. And I should also mention that in particular, the symmetric monoidal structure is given by Day convolution. So Day convolution is a very general thing that you can do. And maybe I'll just say just as an example, like if you had let's say you had two graded spectra, X and Y, and you took their tensor product and you wanted to look at the value at level n, well, this is exactly just going to be the usual monoidal product on chain complexes if you want to, if maybe that's something you're familiar with. It's just given by this. And then there's a similar formula, which is slightly more complicated for filtered spectra as well. but you can be pretty concrete about what these things look like. And more generally, day convolution is something that you can do. So maybe more generally, if you have I, a small symmetric monoidal category, then the categories of functors from I to spectra is again stable, presentable, and symmetric monoidal with this day convolution product. So has all the same properties. And so more generally, if we wanted to, we could, if we had some indexing category that we liked and we wanted to think about I-shaped diagrams in spectra, we could just as well think about like, I filtered or I graded spectra, depending on whether or not I is discrete or not discrete. And maybe that's like the distinction I want to draw. If I happens to be a discrete category, then you're going to say I graded. And if it's not discrete, you'll say I filtered. And I think this is a very reasonable, distinction to draw. Okay. So, just as maybe as one more remark, you don't actually need I to be symmetric monoidal for a day convolution product to exist. It actually suffices, so it suffices that I is what's called promonoidal, which essentially means that what do I want to say? There's a technical way that you can spell this out, but essentially this amounts to like taking some sort of symmetric monoidal structure on the presheaf category associated to I, and then restricting it to I by some nonsense. And it turns out that this is really useful in certain cases. Like, for example, the category delta op is not a monoidal category because it doesn't have it is if you work with the augmented version, but it's not monoidal or symmetric monoidal, but it does happen to be promonoidal. And so you can make sense of so maybe what I'll just say really quickly is that in this case, you can put promonoidal structures on delta op with the property that when you consider the associated day convolution category, that's the same as the pointwise product on simplicial spectra. And this is useful technically because sometimes it's really easy to say stuff like, I have a map between symmetric monoidal categories. I want to think about things like restricting along that map or left con extending along that map. And those kinds of maps have good lax symmetric monoidal properties. And so if you can sort of include some funny examples in this promonoidal land, it becomes a lot easier to sort of work formally with the machinery you're used to from considering day convolution on just ordinary symmetric monoidal categories. Sorry, this is a bit of an unplanned aside, and it's maybe not super relevant. But one other maybe funny example to write down is that if G is an abelian group, then you can consider things like functors like this, and you could think about these as spectra with a G grading, for example. And there, the tensor product is basically very similar to the tensor product of maybe I'll just say Z graded spectra, but now you just replace elements of Z with elements of this group G. And it's maybe slightly more complicated or weird depending on the group structure, but whatever. Okay. So at this point, maybe I just want to ask, are there any questions? Do people have comments? Or just before we totally shift gears for a second? Okay, seems like no. Great. So now I want to talk a little bit about Hochschild homology. And maybe and THH, I'll say. So here's basically how I want to like set things up. So what we're going to do for the following definition is we're going to fix some, nice symmetric monoidal category C, and we're going to think about, some algebra in this symmetric monoidal category. And algebra, of course, means like E1 algebra or like coherently associative algebra or given such a thing, you can always form the following simplicial object. And it's given as follows, or maybe I'll just write it like this. The Hochschild homology of A, with respect to this category C, is given by forming the cyclic bar construction, which is something you can always do when you're given an algebra in a symmetric monoidal category. So you start by putting A in degree 0, you put A tensor A in degree 1, you put A tensor A in degree 2, and so on. And of course, all of these tensor products are just the underlying symmetric monoidal product on C. And then you can sort of, by some sort of universal technique, you can write down the cyclic bar construction. And what you end up getting is some diagram which looks like this. If you've never seen this construction before, all of the face maps are just given by multiplying adjacent factors of A, using up some of the algebra structure. And then the last face map is given by twisting the last copy of A around from the last factor to the front, and then multiplying those two factors together. And additionally, each of these terms in the simplicial object have actions of cyclic groups. And these are compatible with the face and degeneracy maps in the sense that they prolong to an object in concyclic category. So, this whole thing is really a cyclic object in C. And a great fact observation, which comes to us from, so funny enough, sorry, this is totally random, but I was talking with Tom Goodwillie last week, and I asked him, like, hey, who originally observed that cyclic objects give rise to circle actions? And he told me that apparently him and Marcel Bachstedt were listening to a talk by Lodé somewhere in Germany, I think in the 80s. And then they went out to lunch, and then they observed this sort of famous observation. So I thought this was like a really cute piece of like math history. And so this lives in the category of this has a circle action, meaning it prolongs to a functor from BS1 into the category C. And this is really nice. We like actions by groups, and when you have actions by groups, you can do more fancy constructions like homotopy orbits, fixed points, Tate construction, you have a canonical map, you have all that good stuff. And so maybe just to give a couple of examples where the category C varies, so if C is equal to maybe the derived category of the integers, or more generally, the derived category of some commutative ring R, then this gives rise to sort of the classical quote unquote theory of maybe Hochschild or Shukla homology. And this is really closely connected. So maybe I'll just say which is very closely connected. Can't spell. This is closely connected to things like algebraic differential forms and the cotangent complex. And there's like a really beautiful classical theory of these invariants. And if you want to go learn about this stuff, I'd really recommend reading Lodé's book. It's like still one of the best references out there, despite it being like slightly old. Okay, and then in the category of when C is the category of spectra, sort of by this vision of originally conjectured by Waldhausen and Goodwillie, there should be some sort of analog of Hochschild homology in the category of spectra, and this gives us THH, which is a super I guess these days a very like famous and kind of hot invariant due to its applications in p-adic Hodge theory and applications maybe to algebraic K theory and kind of chromatic homotopy theory, stuff like this. So this gives topological Hochschild homology. And sort of this is very famously related to algebraic K theory. And you have this map called the Dennis trace, which goes from the K theory of A to THH of A. It's not a great approximation to algebraic K theory, but it's like good enough for some purposes. For instance, you can use this map, or I should say Bachstedt originally used this map to deduce that, various homotopy groups of the K theory of the integers must be non-zero because it has to surject onto some non-zero classes in THH of the integers. I think this goes back to work of his in the 80s, and this was kind of revisited by Rognus in a published form. And so, I would sort of be remiss if I didn't tell you a little bit more about this THH stuff. So, in addition to a circle action, THH has a much richer structure. THH is also a cyclotomic spectrum. And this just means, and apologies to anybody who does genuine equivariant homotopy theory in the audience and you really like that perspective, this just means that there are some maps called phi p, which go from THH of A to THH of a Tate CP. This thing here is the CP Tate construction. And it's some sort of, maybe spectral analog of some sort of spectral analog of Tate cohomology from algebra. And here we ask that this map is S1 equivariant, where we put the usual S1 action on THH of A, and then we give the S1 mod CP action, which we can then identify with S1 via either the Pth power or the Pth root map. And so we ask that these maps are all S1 equivariant, and we have one of these for every prime P. And the reason we like this is we can use this extra structure to build the topological cyclic homology of A, which is an invariant that's, again, pretty famous. And this is a much better approximation to algebraic K theory than THH is. There are also a bunch of other cool theories that we can associate to the topological Hochschild homology of a ring spectrum. We get this, TC minus thing, which is just THH of A, homotopy fixed points with respect to S1. We have TP of A. This is THH of A, Tate S1. And then, there's not really a great name, but there's also the often forgotten and not funnily named homotopy orbits with respect to the circle action. And so you can do a bunch of these different constructions, and the first two of these things are are involved in the definition of TC and are oftentimes really used to compute TC. So takeaway, if you've never seen the cyclotomic structure stuff before, it's basically like extra stuff laying around that we can use to cook up more invariants, which are better approximations to algebraic K theory. Okay, so here's the next example, which I think will kind of be the star of the show for the remainder of the talk. This is basically going to be what happens when C equals filtered spectra, or C equals graded spectra, or maybe C equals like maybe G graded spectra or something like that. So these are the examples that we're going to be kind of interested in, because these are all symmetric monoidal categories. And so if you have an algebra in one of these categories, maybe I'll just say really briefly, an algebra in filtered spectra is essentially like, some filtered object with multiplication maps that add the filtration degrees together. So you have a multiplication map, and you should think about the Whitehead tower as the canonical example of this. You go from like the ith connective cover tensored with the jth connective cover to the I plus jth connective cover of a ring spectrum. And so you can contemplate versions of THH here. And so these give rise to kind of different theories. So maybe I'll call the Hochschild homology in this category, I'll call this THH fill. So this is like filtered THH. Maybe I'll call this THH gur. And the idea is all you're doing for both of these things is you're just starting now with like a filtered algebra, and you're doing the cyclic bar construction with respect to day convolution. And this is nice for, well, I'll tell you why this is nice in a couple of reasons, or in a couple of moments. So same thing here. So you're basically just forming the cyclic bar construction in a new category. And this will live in filtered spectra with S1 action. This will live in graded spectra with S1 action also. Okay, and why might you want to do this? And here's essentially the reason that you might want to do this. So maybe I'll just call this comparison theorems. This is all folklore, by the way. So here are some comparison theorems. So let's assume that we're given, how do I want to do this? Let's say we're given a ring spectrum A that we're interested in, and we're given a multiplicative filtration number. So I'll just call it like fill upper star of A. So this is like some algebra in filtered spectra. So for example, if you wanted to keep a particular example in mind, you should keep in mind the Whitehead tower of a ring spectrum. That's always going to be one of these algebras in filtered spectra, and it's going to be a filtration of A. Like if you take the colimit over that big diagram, you get A back, and the associated graded is something relatively nice that we have a better handle on than just the ring spectrum itself, maybe. And so here are some comparison theorems about why these are useful invariants. So the first one is that if you take the colimit over THH fill of this filtration on A, this is the same thing as THH of A. The second one is if you take the associated graded of filtered THH of fill star of A, then this is the same thing as the graded THH of the associated graded of A. And moreover, maybe I'll just say like, maybe what I want to say here, and maybe like 2A is additionally, this is a graded spectrum, and the underlying spectrum of this thing is given by THH of the associated graded of A, which is a bit of an abusive notation. But here by this, I really just mean something like the sum over all the gur i's of A, as I lives in C. And so what are these comparison, and maybe I should say that this is as spectra with S1 action, as spectra with S1 action, and as we'll see in a moment, these equivalences actually upgrade to involve more structure, but I haven't told you what that extra structure is yet. So the reason you might want to do this is that if you have a particularly nice filtration on a ring spectrum you're interested in, then this filtered THH and this graded THH are constructions that you can do to try to, again, interpolate between information that you understand and information that maybe you have less of an understanding of. Okay, so, all right. Now so I said something and I need to, qualify this. I sort of said that these are equivalences with respect to more structure than I've actually told you about. So we know that just because we're doing a cyclic bar construction in these symmetric nodal categories, we always have circle actions. But you could just as well ask what happens with the cyclotomic structures. Is there something that happens to that as well? And the answer to that is yes. So question, cyclotomic structures. And basically the answer to this is yes, we get those. And this is sort of an observation originally due to Morten Brun back in, I think, the early 2000s. So you have to be a little bit careful about what you mean, though. Maybe I will describe the situation just for filtered THH, and then you can kind of work out what the analog of that will be for graded THH, just to save a little bit of time. So let's think really quickly, so the maps that we wrote down involving the cyclotomic structure up here, one way you can kind of think about these things is as like certain Frobenius maps. And what we know is that when we take maybe a filtered or a graded FP algebra, the Frobenius map will always multiply the degree of an n homogeneous term by p. So like the pth power of A, if it has degree n, will then have degree p times n. And so we should also expect our Frobenii in cyclotomic, like the filtered analog and the graded analog of these Frobenii, to change the filtration degree. And this is exactly what happens. So basically, this is again kind of another folklore type theorem, which basically says that if you start with some algebra in filtered spectra, then you basically you end up getting phi p, where now we go from the filtered THH of A star to what I'll just write as the filtered THH of A star Tate CP, but now you multiply the filtration degree by P. So this is exactly what we would kind of expect, like from the world of algebra, if we legitimately have Frobeniuses or Frobenii, and that's exactly what we get here. And again, this is going to be this is S1 equivariant. This is S1 mod CP, equivalent to S1 equivariant. Sorry, my tablet just went kaput really quick. Let me try to. Okay. Sorry, one sec. Okay. This is a good time for questions. Does anyone have any questions?
I guess I have a way vague question.
Yeah.
You can think about like modules over the weighted tower of an algebra at like a deformation between modules over the algebra and the associated graded. So this folklore theorem at the beginning is like saying that the filtered THH kind of respect this deformation, that filtered THH is like a deformation between the normal one and the associated graded one.
Yeah, exactly. And I think like the technical reason for this is that all of these functors I've written down are symmetric monoidal. And because they're all symmetric monoidal, like whenever you have a symmetric monoidal functor between symmetric monoidal categories, that will interact extremely well with the Hochschild homology. Basically, you kind of know like from the jump, and I guess you need like sifted colimit preserving or some like that,
sure.
But whatever. Yeah, but you always have an interchange map between different Hochschild homologies when you sort of change the coefficients that you're working with. But then when it's symmetric monoidal, then this is always an equivalence. And this happens to be the case for the associated graded functor, for the colimit functor, for the underlying functor going from graded to spectra. And so this is why all that crap works.
Nice. Okay.
For instance, though, like this fails pretty miserably if you start to like throw in things like homotopy fixed points or Tate or TC or things like that. And so you don't have these nice comparison theorems. You have to add extra conditions in order to get the answers that you want out at the end, basically. Yeah.
Thank you.
But ultimately that should amount to something like the underlying ring spectrum is connective, and or maybe like your filtration is constant after some stage, and like you have some good connectivity estimates on the term tending to infinity. Something like that. Like something like this will usually allow you to prove some sort of comparison for like the, for like the homotopy fixed points, for instance. Yeah. Okay, yeah. And anything else while we're still paused? I managed to get the screen working again, I think. Is that, can everyone see it?
Yeah.
Okay, fantastic. Okay, so right. So maybe maybe the thing that I'll just add here is that like this cyclotomic, this like filtered and graded cyclotomic structure essentially comes from some sort of analog of the Tate construction, which or sorry, the Tate diagonal, which is a map that exists in spectra. It goes like, you know, from the identity to the pth power and then Tate CP. And this has like lots of really good formal properties. And essentially the key point in like actually proving that THH fill and THH gur and all these other things like have this residual structure is producing an analog of that. But now, you know, you have to shift the filtration degree. And basically the way you go about doing this is kind of an elaboration on the way that, for instance, like Nicolaus and Schulze go about producing this Tate diagonal with all its sort of residual structure and, you know, its universal property as some sort of, you know, unit like canonical like lax symmetric monoidal transformation, something like that. And maybe I'll just leave it at that. So produce some analog of this. Okay, and now, you know, okay, now that I have like 7 minutes left to tell you stuff, I wanted maybe talk about some actual examples of using this structure to do stuff, because I've just told you a bunch of nonsense, and you know, it would probably be good to explain why this stuff can be useful and how, like, what sorts of things you can do with this. So let's do some. Maybe I'll just say examples. I would like to title this extended examples, but I don't think I'll have time to like really say a ton of things. So the first example I want to talk about is what's called the May filtration. So originally this was constructed by, I should say, Angelini, Knoll, Gabe Angelini Knoll, and Andrew Sauch. They wrote this nice paper. I think it came out in like 2018 or something. And basically what they do in this paper is they define a filtration on the THH of a ring spectrum, and it's done in the following fashion. So here's a definition. So given some ring spectrum A, you can define the May filtration on THH of A to be the filtered THH of the Whitehead tower of A. And so right away, like, this seems pretty nice by all of the like comparison theorems we just sort of talked about previously. We kind of know right away that the colimit over this May filtration, so like the underlying spectrum, this is given by THH of A, essentially because we know that the underlying spectrum of the Whitehead tower of any ring spectrum is the ring spectrum A. And then we also know that the associated graded of the May filtration, and I'm going to like conflate the underlying and the actual like graded spectrum a couple times here, so I apologize for the abuse of notation. So this is actually given by the THH of H pi star of A, which is the generalized Eilenberg-MacLane spectrum associated to A. And if this, you know, if A is a ring spectrum, then this will also be a ring spectrum. Basically, by some of the stuff we sort of already said, pretty much the Whitehead tower is lax symmetric monoidal, and passing to associated graded is also symmetric monoidal. And so this induces a ring structure on the generalized Eilenberg-MacLane spectrum associated to A. And just really quickly, maybe the sort of the one line like why this is useful is that, you know, if you have a ring spectrum whose Whitehead tower you understand, this can kind of allow you to take information about THH of H pi star of A, which is sort of an algebraic thing that's closer to algebra than the ring spectrum A itself. And then you can try to use this to prove stuff about THH of A. And just as like a sample application, here's a theorem. And this So in this result, I sort of critically use the May filtration to like establish the following fact. So if A to B is a faithfully flat map of connective E2 rings, then there's an equivalence THH of A with this limit of THH of B tensor A plus 1. And this is an equivalence of cyclotomic spectra. And in particular, this tells you then that same is true for TC, TR, TC minus, TP, etc. It turns out. And the idea, basically the idea of the proof here is something like, this is a theorem that was proved in the discrete case by Botmore and Schulze. And by sort of going from, you can kind of, by a series of reductions, you can essentially reduce this theorem to the question of the generalized Eilenberg-MacLane spectra, and then by some May filtration argument, and then you can go from that to the discrete case by doing something called like one connective descent, which I can say something more about if people are interested in. But the idea is basically that if you've got like a map of rings or E2 rings, which is an iso on pi 0 and is a surjection on pi 1, then you have this kind of descent limit property for those maps also. And of course, if you have a connective ring spectrum, then the map from H pi star of A to H pi 0 of A is one connective. And so you can sort of you basically do descent for a different kind of map, and then you do some May filtration nonsense. Okay. And then really quickly, I will just kind of, squeak through this like second example, which has to do with twisted group rings. So really quickly recall that if R is a ring spectrum, or maybe just an ordinary associative ring, then we can form something called the group ring on R, which in the case of spectra is given just by taking the smash product of R with the suspension spectrum of G. And this is frequently denoted by S adjoin G. This is the spherical group ring on your group G. Here, G is just some discrete group, let's say. But there is an analog of this construction in the case where, R, let's say R is an object in, it's a ring spectrum, but it has an action of this group G in ring spectra. So it's acting by maps of rings. Then you can form a different construction, which is called R sort of angle brackets G. And this is called the twisted group ring. And maybe just really quickly, it has the same underlying spectrum as the group ring, but the multiplication is different. So because this has the same underlying spectrum, it basically looks like kind of it looks like a direct sum of copies of R over the elements in G. And you have a funny multiplication, which I'll try to describe in a sec. Basically, you have a term here, looks like A comma G, and you have A prime comma G prime. And I always get the order of this messed up. So let me just quickly look at my notes. Okay, and the multiplication is given by A G of A prime times G G prime. And what is this term here? This basically just means we're taking the automorphism of R, the ring automorphism of R associated to this element G, and we're applying it to A prime, and then we're multiplying these terms together. So there's kind of like a twisting of the multiplication. And essentially what you can do, and if people are interested, I can say more about this like during the question and answer or the question section. But basically what happens is you can put a G grading. You can put a G grading on R adjoin G, which I'll call GR like this. And if you take the graded THH, or I should say the G graded THH of this graded ring spectrum, this produces a kind of grading on this produces some sort of like G-graded cyclotomic spectrum. And when you pass to the underlying spectrum, this exactly gives you the THH of this twisted group ring here. And this sort of, maybe I should just remark really quickly that this extends some work of Vera, who showed that if you have an ordinary ring and a group action by ring automorphisms on that, there is a decomposition of the THH of the twisted group ring into like into a sum of terms, which basically amounts to just giving the thing a G grading. And so this sort of generalizes that work. Vera only proves that in the case, he only shows that this is an equivalence of things with circle action and doesn't deal with anything like the cyclotomic structures. And so maybe I'll just end my talk here, but these are just like kind of some sample applications of these things. And I can go into more detail about why maybe this last example is interesting if people would like to hear about that. So thanks a lot for your time.
Very much. Is there any questions?
I have another like vague question.
Yeah.
Related to the last one, I guess.
Yes.
It seems if you're interested in like synthetic spectra, for example, it's natural to try this in like the synthetic setting and see if you can compute more things about spectral THH by using like synthetic methods or something. Is this something you have thought about, or?
Yeah. So maybe I'll say. So maybe let me repeat the question back to you and see if I understood correctly. Are you sort of saying like, could you do some kind of THH construction in synthetic spectra and then like relate that back to ordinary THH? That's sort of the thing you're going for? Okay. Yeah. So the answer is, okay, so this is a great question for a lot of reasons. So I want to maybe just like, before I get to the case of synthetic spectra and say something about that, I want to start by thinking about what that question is, what the analog of that is just for the Whitehead tower, for instance. So what did we do with this May filtration, right? We kind of took this filtered THH of this guy here, and we did a cyclic bar construction. On the other hand, what you could have done is you could have taken this thing here and you could have said, well, what if I just did that on the outside of THH of A? And these are going to be very different things. For example, like it's not